All right, welcome back. Mic check. So I'm in the red. Let me put that down a little bit. Okay, that should be better. So this is going to be part two of applying to Aigo.ai. Aigo.ai is a AI company, and I've mentioned many times before on this channel my beliefs regarding AI. They come from a PDF called Situational Awareness, written by Leopold Aschenbrenner. And I believe 2027 is going to be a really big year for AI in that it's going to be basically the year that the race to so let me put it more simply. I believe AI is going to become a multi-trillion-dollar industry, and it's going to become that very quickly. I believe 2027 is going to be a big year for AI when it comes to the race to have the most powerful AI. That will where we'll see a lot of changes happening in society, and I believe that if AI is the next big thing in tech. If you don't want to be left behind in tech, as I kind of feel like I was when it came to studying network engineering and working at an internet service provider for 6 years during the rise of cloud, you gotta kind of get ahead of the curve in AI. So this is basically the best opportunity I believe anyone has to become involved in AI, because if you look at the trend lines, like ChatGPT just came out recently. ChatGPT, as of like last week, released a $200 tier. Before that, it was a $20 tier, and before that at all, it was just like a dinky technical demonstration. So it's beginning, right, and it's the worst it'll ever be in history. And the big thing that the why there's this race right now, this race to the $1 trillion cluster, as that said before I accidentally closed it, is they want AGI. They want artificial and general intelligence that can do a wide variety of things with very little or no pre-exposure or training. They want it to be able to be as functional, if not more, than a human. And then they want it to be able to be downloadable into a form factor, like a robot or something like that. And they want to have a worker, have something that can replace human workers. But more than that as well, like they want AGI for other reasons. I mean, you can think of it intuitively. Like, imagine if you I think people who have gone to college, getting a chance to talk to your professors, to talk to your other students that are really some of the brightest minds you've been exposed to so far in your life, that can be really exciting. Just recently, I played in my community orchestra with a viola professor, and I got to see a piece I'd been working on in my childhood play to perfection, and that's exciting. So you can have that in your pocket on your phone. You can have the brightest mind you've ever talked to in your life, giving you advice and helping you achieve your goals. That's it's very easy to see why companies are spending so much on this. And you can imagine, in contexts like military designs, you could have a team of you could have a small army conquer the whole world if it's led by the most intelligent general ever to exist throughout humanity. Like, there's all kinds of examples throughout history of small armies winning because they had superior intellect. And let's get a few from ChatGPT. Give me a few key examples of small armies winning major battles because they had superior intellect. So, Battle of Marathon. Yeah, I don't know my history that well, but basically everything I'm saying now kind of is my own interpretation of what I've read in Situational Awareness by Leopold Aschenbrenner, and it's why I believe AI is so important and why so much of what you see on my channel now is basically all AI. Like I'm applying to this AI company. I'm working on my own AI project with Drew Brown, who needs to be on this channel. I'm sorry he has not been. I was reading a book on the mathematics for machine learning. So it's been all AI since about this month so far. So. All right, so let's continue this job application. So the job application was announced in a LinkedIn post, and the LinkedIn post was created by the owner of the company. I'm not sure. I'm actually not sure if he's the owner of the company, but it's a very fascinating character named Peter Voss. So most people in their 70s, I think he's probably in his mid 70s. Oh, and he's not on Facebook. He's on LinkedIn. Most people in their mid 70s, they're retiring. They're not, kind of in the heyday of their career. So he's from my understanding, in his mid 70s and sharper than ever, working as the CEO and chief scientist at his company that is on a mission to bring human level AI to the world. So very fascinating character, super thin guy, unlike me, because he's all about science and the science of longevity is calorie restriction. So he has some fascinating articles up on his page. Optimal.org is his domain. So he's all about the science of optimization, living optimally, which I like. It looks like his site is down now, which isn't optimal. But when it was up, there were good articles. He's all over the internet. He's a big figure. This is not him, by the way. This is somebody else. He has a kind of unfortunate first and last name, and is from Germany. But his site, from what I understand, is this optimal.org. But unfortunately, it looks like it's down. Oh, now it's up. Okay, great. So so if you go down to his, I think it's other links. So he's in longevity, which is kind of a fascinating topic because there's a lot of research out that seems to be pretty definitive when it comes to longevity. The main thing that seems to be pretty airtight is calorie restriction. So he has a FAQ on that. He's doing that seems to be one of his main strategies. All right, so yeah, very the opportunity to work for a specific person that when I read his ethics, philosophy, helpful this is stuff, I'm always like yes, that is a opportunity that I think makes sense to jump on. So let's take a look at the job post again. So he's looking for an AI engineer. So this will go in my work search activities log as applying to become an AGI engineer. So let's look at the job post. And then I did verify. He said it's fine to submit the application by Friday. So let's look at the application, and I just need to get it in by Friday. So here's the application. So all you need to do is review the articles and white paper without an S, which is very unclear because there are 3 white papers. And then email your top 3 questions along with why you believe you'd be a great fit. So I've got an email template going here. The first thing I'm going to do is show him everything I read. So here's the application email template. So I'll send him this here. So reviewed white papers. I'm going to try to review all 3 of the white papers on the site. It says it says to only review one, but it doesn't say which one. So hopefully I'll have time to review all three. And then it says to review the articles. The articles are, I think, pretty short, so that should be pretty easy. And then this is the big one that I'm doing now. Multiple chapters, probably like 25 pages of reading. The other ones are a lot smaller, so I should be able to get this in by Friday. So I'll send him a link to this playlist of me reading everything. And then I'll send him this email, this filled-in email template. So it'll show what I've reviewed. It'll show my questions, and then it'll explain why I'd be a great fit. And I feel like I can let me work on that section now as well. So let's open a new So let's do this, and then let's talk to the AI a bit and get a sense of that. So. Hey, and hold on a second. So let me refresh that. Yep, and we'll use pro mode for this. I'm paying $200 a month, so I might as well. All right, so I'm applying for a job application. The job is called a AI/cognitive AI software engineer. And the main question of the job post is, are you eager to be a key member of the team making full human level AGI happen? And my answer to that is absolutely yes. So what I need to do is review articles and white papers on the website of the company I'm applying for, and then email 3 questions to them. And then along with that, I need to tell them why I believe I'd be a great fit. So I haven't finished reviewing the articles and white paper yet. I do have one question that I'm working on, but I don't have all 3 yet. And then, but what I think I probably could do now, before I review everything and before I come up with the 3 questions, is get kind of a rough draft going for why I believe I'd be a great fit. So can you kind of help me think about that, have a discussion with me about that? Because I feel like I could get this done or going now, and I feel like this would be a good place to start. So when you're ready, let's start with kind of like why I wouldn't be a great fit, and get that out of the way, and then we can come up with, we'll start there, and then we'll talk about why I would be a great fit afterwards.
Sure. Let's explore the potential reasons you might not be a great fit so that we can understand and address them when we craft the possible pitch. The idea is that by looking at possible gaps or concerns first, we'll clarify how to position your strengths and readiness for the role later. So let's walk through a few areas that might raise questions. 1. Depth of technical expertise. Maybe you haven't worked directly on full human-level AGI before. And honestly,
well, there's no such thing. Yeah.
Or your experience is more in traditional machine learning rather than cutting-edge cognitive architectures. Perhaps you've done a fair amount of AI engineering, but not specifically building systems that emulate human cognition or reasoning, which could be a unique skill set. 2.
All right, so I'm just going through this and say, okay, yeah. Yeah, those are some good ideas, but you know what? I'll tell you. Like, you don't have to tell me or give me ideas. Like, next, what I'm gonna do is give you the post itself, and then I'll tell you like what I think my limitations might be. Are you ready? I mean, these are good ideas.
Sure, I'm ready. please go ahead and share the job post. Great. I have the full posting in front of me. Go ahead and share your thoughts on where you see potential limitations or concerns. And after you outline those, we can discuss them together.
Perfect. So yeah, the main thing I see is that their platform is in .NET Core / C#, and I'm a Python guy, and I'm not really a developer. I'm more of a network engineer. I held the CCNP and I held the JNCI SSP. I worked at a service provider for 6 years. I attempted the JNCI ESP. So, I know all about routing and switching. I know all about really kind of specific expert level ISP sorts of things. I worked at the fiber side at the ISP, not the DOCSIS side, so I know all about CWDM, DWDM, multiplexing, those sorts of things. I know all about cell tower backhaul installs. I know all about EVPNs and VPLS. I worked with ISAS, worked with BGP. I worked on the edge of the network. When I started, I did turnups. Then I did more head-end sort of configurations. I did a lot of configuration. I was on the actual devices, hands-on on the devices. I worked with techs when I started, technicians, on the phone with technicians. Then later I kind of worked with more getting things ready, like taking the design, reading, interpreting the design, applying the configuration the design called for, like evaluating, reviewing the design, sending it back if it needed to be. I worked on like adding, onboarding devices, adding them to, statistics platforms, some troubleshooting stuff for sure. Making sure that the statistics show up in programs like Sev1 and stuff. So definitely some troubleshooting, especially because I did a lot with Ethernet CFM, like a lot of Ethernet CFM sort of stuff. So like if it didn't show up, if the CFM connectivity fault management, wasn't going, like I had to troubleshoot that. So I did a lot of like troubleshooting with that. I did a lot of testing as well, especially when I first started, RFC testing, EtherSAM testing, pseudo wires, MPL pseudo wires. I had to pull those out, reconfigure pseudo wires for testing to the tester. So a lot of really complex testing as well. So I did a lot, and that was early in my career. Later, I did a lot at the service provider in the first 6 years of my career with automation as well. And I did that all throughout. I was always trying to automate things, and for my last year at the service provider, I was on an actual automation team. And then since leaving the service provider, I worked in jobs involving automation more specifically. So, I'm a Python guy, right? So that would be like my first limitation possibly, is I'm less of a developer, and kind of definitely when it comes to the sort of developer I actually am, it's really not a .NET Core or a C# developer, but it says that basically all they need is a minimum of 2 years of work experience, which at this point I'm almost going into my second decade. I'm almost at the 10-year mark. It says prior AI experience is not required, since it's fundamentally different. It says you don't need expertise in full stack, communications, cloud, or security either. It says the focus is heavy duty algorithmic design, development, and debugging. So, I had to do a lot of sort of debugging sort of things. a lot of kind of creative development, trying to develop things that really hadn't been developed, then trying to automate things that hadn't really had a good, clear solution for automation before. I had at least one major accomplishment where the higher up engineers said something couldn't be done, looked at it and decided that it could. The example of that is on my resume. It's changing the BOF file. It's called BOF, which is the it's a file on the Alcatel Lucent, so that when the device boots up, it boots up with a valid configuration. Like, I figured out how to do that with a coworker, and even though we were not the head honchos, we were able to do something that was thought not to be able to be possible to be done, just because we spent more time on figuring out what that file actually was for and does. So like, I'm capable of strong analytical thinking and logical problem solving, for sure. So that's the first limitation. So let's start there. Let's check in briefly, and then let's talk about the rest. And it looks like it stopped recording my voice. Yeah, and I'll be working with it.
Like the core limitation you're identifying is that your background is more rooted in network engineering and Python-based automation, rather than in the specific software development stack and cognitive AI environment this role is asking for. Let's break that down a bit. 1. Language and platform familiarity. The position emphasizes .NET Core.
I wish you could make them talk faster. Anyways. Oh, you know what? I can. We can turn this off, and then we can use the voice that I prefer.
It sounds like the core limitation you're identifying.
It sounds like the core limitation you're identifying is that your background is more rooted in network engineering and Python.
I prefer that voice.
In the specific software development stack and cognitive AI environment this role is asking for. Let's break that down a bit. Language and platform familiarity. The position emphasizes .NET Core, C# for algorithmic development, while you've spent the majority of your career in Python. Even if you've been coding for automation, Python and C# have different ecosystems, libraries, and paradigms, especially when it comes to low-level algorithmic challenges. This can raise concerns about how quickly you could get up to speed in a .NET environment. Domain focus, networking versus cognitive AI, much of your experiences in network engineering, configuring devices, working with complex ISP protocols, technologies, multiplexing, and various testing frameworks. These skills, while highly specialized, may not directly translate to designing cognitive architectures or solving the abstract, logic-intensive problems that AGI development might pose. The role suggests a deeper need for conceptual thinking about intelligence, cognition, and algorithmic reasoning. You mentioned debugging complex systems, but that's often in the context of network paths or protocols, rather than understanding logic or data structures that simulate human-level reasoning. Algorithmic and cognitive problem solving versus infrastructure-focused problem solving. While you've done a lot of creative problem solving in network automation, inventing new testing methods, automating tasks, troubleshooting connectivity, fault management, the job at Aigo.ai is likely to center on designing, refining, and debugging algorithms that replicate aspects of human cognition. It's a different domain of complexity. You may have less direct experience tackling abstract computational modeling of intelligence or large-scale AI problem solving, which could be considered a gap compared to a candidate who's done more with AI research, theory, or development, even though it's stated that prior AI experience isn't required. Cultural fit with a high-level R&D environment. Although not directly stated as a limitation, there might be a cultural shift. This company seems to be on a mission to achieve AGI, which might require a high degree of theoretical exploration, comfort with ambiguity, and deep involvement in fundamental research, very different from a more operational network engineering focus. Adapting to a research-oriented mindset could be a challenge if most of your experience has been on the practical infrastructure side. Would you say these points capture the main limitations you see? If there are others you're concerned about, let's identify them. Once we've got a solid view of these potential gaps, we can discuss how you might frame your strengths and adaptability to turn them into selling points.
Yeah, I mean, those are pretty much that's a good summary of the main limitations. Yeah, that's a good summary of my main limitations. I mean, honestly, I wouldn't be working so hard on this, trying to get this in by Friday, if I thought I had a lot of limitations. Like, I think those limitations aren't that significant, because I mean it's definitely saying, like, you need to be a brilliant, highly skilled software engineer that thrives on tackling complex software problems. So, I don't know if that, my leak code scores are not very high. I haven't spent a lot of time on leak code, and I don't have, like, a PhD in software engineering. So it's, that might be another limitation for sure. am I deeply motivated to help make AGI a reality? Oh, absolutely. You know, I've been using ChatGPT every day since it was released. I pay $200 a month for it, and I want to solve a lot of problems in my life, and I think an AGI would really help that. I think it would help solve problems, existential problems that broadly affect humanity as a whole. Like I'm a huge optimist when it comes. I'm an optimist and an accelerationist when it comes to AGI, and yeah, I think I definitely am motivated. Do you find yourself fascinated by the nature of intelligence and how the mind works, and comfortable thinking like a cognitive scientist? I mean, again, like, yeah, absolutely. The answer is yes. In fact, I kind of have a bit of a unique history because I have been I've had kind of some unique challenges when it comes to how the mind works, I've kind of had to think a little bit like a cognitive scientist to be comfortable with like taking regular medications and making sacrifices, like, not drinking alcohol, not going out late at night, and prioritizing sleep and prioritizing my mental health. So yeah, all in all, honestly, I feel like this is really a great job for me. So let's move on to the next part of what we're trying to do here. Let's answer that question. Why I believe I'd be a great fit. Let's start with, so you tell me why you think I'd be a great fit. Let's start from there, and let's get a good rough draft going for this.
Sure, let's put together a strong draft focusing on why you'd be a great fit. We'll highlight not only your technical adaptability and problem-solving capabilities, but also your genuine passion for AGI and cognitive science. We can refine this later, but here's a starting point. Draft, why I believe I'd be a great fit. I am convinced that my combination of deep technical experience, relentless curiosity, and genuine passion for achieving true AGI aligns perfectly with your team's mission at Aigo.ai. Although my career began in network engineering and large-scale infrastructure automation rather than .NET Core, C# development, I have consistently demonstrated the ability to master new technologies and solve complex, previously uncharted problems. Over nearly a decade, I've honed my skills creating innovative automation solutions where none existed, debugging intricate systems, and adapting to evolving architectures, all of which required rigorous analytical thinking and a willingness to learn rapidly. Beyond my technical foundations, I am genuinely fascinated by how intelligence works. I've spent considerable time reflecting on cognition, problem-solving, and the nature of human thought. My own experiences, both personal and professional, have led me to appreciate the complexity of the mind and fuel the desire to contribute meaningfully to the development of truly intelligent, human-level systems. I'm not only an optimist about AGI's potential to solve significant human challenges, but I'm also a dedicated student of the field, prepared to immerse myself in the cognitive frameworks and algorithmic approaches that underpin your platform. While I may not have worked directly with .NET Core, C#, I bring a proven track record of quickly adapting my skill set, from mastering complex network protocols to designing robust automation frameworks. When faced with a tough technical challenge, I thrive on breaking it down logically, methodically testing assumptions, and engineering a pathway to a solution. My background in network engineering taught me how to build resilience into systems, to think about every layer of complexity, and to iterate until I achieve the desired outcome, traits that will serve me well in the context of AGI development. Most importantly, I am highly motivated to be part of a team dedicated to building something truly transformative. The opportunity to help unlock full human-level intelligence isn't just another job for me, it's a mission I believe in. I am ready to invest my energy, creativity, and determination into evolving this technology, working closely with your chief scientist, and continually refining my skills to fit the unique challenges of cognitive AI. In short, I bring proven adaptability, strong reasoning skills, a passionate drive to contribute, and a deep appreciation for the nature of intelligence. I'm confident.
Oh, I don't know why it stopped reading it when I changed the... Well, anyways, yeah, that's a good... I'm curious who their chief engineer is, because I thought... Because it says that Peter is the... Oh, no, he is the chief scientist. Yeah. I want to work with him. Like, he's an extraordinary person. All right, so yeah, so I might include that as a temporary there, but the most important thing I need to do, which I'm kind of I'm half an hour in and I still haven't started it, is get all the readings done. Okay, so yeah, this is a lot. So I made it to chapter 2. And the cool thing about this is great. Like this is really bringing me up to speed. So yeah, let's just try to get all these readings done. So this is chapter 2, related work. Section 2.1, continual learning. And just to briefly summarize the main points that I remember reading before, this was about 2 days ago. And it might be hard for me to do that. So catastrophic forgetting, which is abbreviated to CF in this reading, is kind of one of the coolest things I learned about that I did not previously know about. And that's one of the big limitations of the current path to AGI is it can't remember everything. So especially near the middle of its context window, it'll catastrophically forget. Yeah. Okay, so one thing I was doing a wrist strengthen or a finger exercise, finger strengthening exercise. But so if the distribution space shifts, new modeling should expand this shift. If the initial space is merely shifted instead of adjusting the size of the distribution space, then catastrophic forgetting will occur. So an idea I had for my first question would be, what is the limitation of the current models when it comes to catastrophic forgetting? Is RAG and a memory system enough to overcome this limitation, or is the fundamental concept of having a model pre-trained something that causes catastrophic forgetting to always be an issue? So that would be a good question, I feel like. So with that in mind, let's go on and continue reading. So this is section 2.1, continual learning. I'll do a sound check and okay, good. Sound is still recording. So continual learning, CL learns new emerging tasks efficiently while mitigating CF in LLMs. And CF, remember, is catastrophic forgetting. The existing work on CL can be classified as follows. And these are cited in the citations at the end. Number 1, consolidation-based methods such as regularization or distillation protect important parameters from significant shifts. They do this by aligning the current output space with previous ones, distillation loss, or restricting the model parameters by estimating loss or averaging weights, regularization loss. Weight regularization concerns parameters, whereas function regularization influences behaviors of the existing model. Weight regularization selectively regularizes variation of neural networks parameters. It typically penalizes each parameter's variation based on its importance in performing the previous tasks. Function regularization is a robust approach targeting the model's in-between results or the prediction. It typically implements knowledge distillation, which is abbreviated to KD, by learning a small student model from a large teacher model previously learned to mitigate CF. The student model can learn from new training examples, replay previous examples, and use available unlabeled data or data generated from previously learned tasks. Aside from regularization, some methods focus on error optimization, such as calculating gradient propagation on the old task's input data. I think EG is, in other words, rectifying the current gradient directions through parameter updates. Meta learning of arriving tasks. So, in other words, obtaining an inductive bias for new tasks internally rather than specifying it explicitly. Yeah, IE is... oh, no. EG is, for example, IE is... in other words. Okay, yep. All right. So, for example, so meta learning of arriving tasks. For example, obtaining a inductive bias for new tasks internally rather than specifying it explicitly, and investigating loss spaces. For example, discovering a local minimum by adjusting the training variables, including learning rate, decay, dropout rate, and batch size. And I am familiar with some of those terms. Those are very technical jargon terms when it comes to AI. Local minimum means, let me explain local minimum. So we have a graph here, and we have let's say we have somebody has we'll call this Apple sales. Okay, and then we'll have time here. And then we have apples. So so that, yeah, then we just have, you know, through time, and then we have the number of apples. So so here's what our sales figure looks like. Oh, sorry, I need just a. So here's what our sales of apples look like over time. We had sales were good. Something happened. You know, it's off season. We don't have fresh apples anymore. They go down. And then sales are good again. Open another off season again, good again. Something happened. Now our sales are doing very good. So like a local minimum would be, like here, whereas like a global minimum would be, you know, like the average of all of these minimums, or like the you know, it's not, you know, or so like you'll have to be careful in determining what the minimum and maximum is. You have to be careful to avoid, or to at least know when you're selecting local versus global minimum and maximums. So like we can see, like, okay, let's say this is 1 year here. So let me do that there. So what was the minimum number of apples I sold? You know, it wouldn't be the this value here. That would be the local minimum for this part. You know, you have to kind of account for the. I'm not sure if I'm explaining that right. Let's just do a brief. Explained in a minute. Oh, and you know what? We can use. Let's use ChatGPT for this. Let's just start here. So I made this drawing to try to briefly explain the idea of a local minimum does the drawing look like it would be useful, or does it seem way off base? And then the next prompt will be briefly explain the idea of a local minimum. Pro mode takes forever. I actually prefer the non-pro mode because it doesn't take as long. And it's like the way I use LLMs, like I don't need it to, like I'm going to cross-reference it with another resource.
Your drawing has the right idea conceptually, trying to show a curve fluctuating over time so that a dip can represent a local minimum, but it's fairly difficult to interpret as is. The overlapping lines, multiple loops, and unclear axes make it challenging for someone else to quickly grasp what's being shown.
Yeah.
For teaching something like local minima, a simpler, more focused graph would be more effective. Here are a few suggestions to improve clarity. Use a clean, single curve, instead of multiple overlapping scribbles. Try drawing one continuous line that rises and falls over time. Clear labeling. Mark the horizontal axis as time, and the vertical axis as apple sales or quantity. Make sure these labels are neatly written and placed near the axis.
Alright, so...
Your drawing has the right idea conceptually, trying to show a curve fluctuating over time so that it...
How do I stop it from...
Your drawing has the right idea.
Oh, I get this. Okay, perfect. So now we're going to have it briefly explain the idea of a local minimum, produce a better drawing. And it's usually really bad at drawings to explain concepts. So we'll see how it does with that. I have a feeling it won't do very well. But anyways, while that's going, let's continue making progress here. So yeah, I just wanted to dive into some of these terms here because these are really like technical jargon terms. So training variables, that's a big one as well, including rate, learning decay, dropout rate, batch size. Those are you know big time jargon. All this is all packed with jargon. So self-supervised learning, generating implicit labels from structured data, and upstream pre-training with downstream fine-tuning, pre-trained representations fixed when learning downstream tasks also belong to this class as they create and employ internal representations in LLMs. However, they require large amounts of data. While these methods may only partially utilize historical data, their ability to safeguard crucial parameters is a significant advantage. So let me use the LLM for this. I'm going to say unpack this, pack the jargon in the following paragraph. Create a table with each jargon term and a brief explanation. All right, there we go. There we go. So now the idea of a local minimum, and we can have the voice read that.
Idea of local minimum. Local minimum is a point on a graph where the value of the function is lower than at all the immediately surrounding points. In other words, if you look closely around that point, just a small neighborhood, there's no other point nearby with a smaller value. It's like a small valley in a larger landscape. Improved drawing, conceptual sketch, explanation of the drawing. The vertical axis represents the quantity you're measuring, e.g. sales. The horizontal axis represents time. The curve generally rises and falls. The dip in the curve is the local minimum. At that point, if you move slightly left or right, the values go up, meaning the particular spot is the lowest in its immediate neighborhood, even if it isn't the lowest of the entire graph. Yeah, so I don't think it did a very good job here. I can make it more simple with my explanation by just doing this. So let me select all this, delete it, and I mean we could just look at this image right here, but let me go like that. There we go. So this right here is a local minimum. If you look at the entire graph, we can see this is actually a lower minimum here. So that's the idea of a local minimum, is you can get into a situation where you think
oh, this is the minimum. But it's the local minimum. When you look at the rest of the data, there's actually a minimum that is more of a minimum than this one, and you mistakenly selected the minimum because you only had a local perspective. I think that can happen quite often. All right.
Brief explanation consolidation-based methods versus the Hilke model. Retain knowledge.
Here's all the technical terms. So you can see like basically every word in that is a big time technical term. But anyway, let's move on. So number 2, dynamic architecture based models. Train a model by increasing its size, number of parameters, with the task number, also known as parameter expansion. These methods include task-specific parameters through a model adaptation by adding task-specific parameters, parameter allocation, creating task-specific modules, modular network, and differentiating shared and task-specific model components, model decomposition. Parameter allocation dedicates a parameter set in the model of each task. The expansion of such models should be balanced with the increase in tasks. Model decomposition separates a model into shared and specific elements. For instance, the parameters can be decomposed by additive decomposition, singular value decomposition, and low rank factorization. So yeah, I'm filled with jargon here as well. A modular network includes modules or subnetworks learning incremental tasks simultaneously without sharing task-specific components. Mixture of experts, MOEs, architectures are examples of this method. We describe them in section 2.4. Visual prompt tuning, VPT, combine, and then the other thing is, these are all linked to citations. So, this 38-page paper, if you read all the citations, which if you don't understand what visual prompt tuning is, I do not. That's probably the next step, is to go and read that citation. So now we're talking about thousands of pages. Combines previous techniques by utilizing lightweight trainable models to adjust the pre-trained model by prepending learnable parameters, aka prompts, to the base features. The model concatenates parameters and features for the vision transformer blocks, encoding task-specific information into the prompts while keeping pre-trained weights unchanged, minimizes the cross-entropy loss. The previous methods have a major drawback: the linear growth of training costs as the model size grows with new tasks linearly. This cost increase can be a deterrent despite their ability to overcome catastrophic forgetting. And I feel like this is another one that screams to be highlighted. So I'll keep that in notes section here. All right, so number 3, memory-based methods keep additional memory of examples of previous tasks, which are used, replayed when learning new tasks. While they retain some information from previous tasks, they face challenges such as overfitting and low scalability due to frequent retraining of the model, aka replay-based or rehearsal-based. These methods typically approximate and reconstruct old data distributions. Experience replay records a small amount of old training examples. Generative replay employs a generative model to produce synthetic examples for training. Feature replay restores the distribution of old features through saving prototypes, and this is in other words, rather than for example. So in other words, feature distillation between the old and new model or representation shift to update the preserved old features. Statistical information, and this is for example mean and covariance, or training a generative model. However, selecting exemplars from pre-training datasets may not be possible and can be difficult, and downstream data may not always be suitable for preserving the pre-training knowledge. All right, so approaches to continual learning, memory-based methods, dynamic architecture-based methods, and consolidation-based methods. So memory-based methods seem to be based on inputs to the LLM. Dynamic structure-based methods are based on the model itself. And then consolidation-based methods is an approach based on the model, the output, and the error. So the research from the paper site in citation number 42 analyzes continuous learning as a continual learning as a multi-stage training in which training objectives are delegated to specific models. Based on the target information updated and distinct LLM-based learning strategies, continual learning can be classified as, number one, continual pre-training, CPT. Expands the model's general natural language understanding and generation capabilities. It conducts self-supervised training to enrich the model's general NLP, natural language processing, knowledge and general knowledge of new domains, such as learning new natural or programming languages, factual knowledge, for example, most recent information, and domain-specific knowledge, for example, e-commerce. Number two, continual instruction tuning, CIT, improves the model's response to specific user inputs. It conducts supervised instruction following, fine-tuning to learn domain-specific tasks. For instance, learning to solve new tasks, for example, code generation, tasks in novel domains, for example, medicine, or to use new tools to solve problems, for example, search engines. And number three, so the third classification for continuous learning is continual alignment, CA. That ensures the model's outputs adhere to human values, preferences, and ethical and societal norms. For example, learning to align to ethical and social norms. For example, culture-specific norms or user preferences. For example, emerging values on new users. The challenges of the previous strategies include training costs concerning computational and human resources. For example, reinforcement learning from human feedback for continual alignment. So you have a person sitting down saying yes or no, this is a good response. That requires a lot of, you have to pay that person, you have to make sure they can produce that task, like you're asking a lot of a person or a team of people to do that continually. Preserving privacy and safety while processing user-generated data and combining different strategies. And then the key thing about RLHF is HF stands for human feedback. So you can't automate that. Like it literally means not using an LLM for that purpose. For example, when the instruction tuned or aligned model follows continual pre-training, catastrophic forgetting may occur, resulting in reduced performance on instruction following or human aligned tasks. I feel like I, as a human being, an organic intelligence, have a lot of catastrophic forgetting. I feel like it happens a lot when I go through a doorway. All right, so I made a bit of a chunk in that, which is good. I'm at about the 1 hour mark. Let me go for another 5 minutes, and then take a Pomodoro style 15-minute break, and then come back. So next part says the research described in citation 46, the catastrophic forgetting, CF, in continual pre-training of the fine-tuned Llama 2 model with 7 billion parameters, followed by supervised fine-tuning and reinforcement learning from human feedback by comparing outputs for different alignment techniques. During alignment, the study employed various techniques to prevent CF, including freezing specific layer models, freezing specific model modules, for example, self-attention and FF modules. I don't know what FF hasn't been explained yet. The model adapters, is this like foundation models? Let me get that. It might even be in this jargon already. No. Oh, it says it right there. Feed forward modules. All right, so, and model adapters including additional trainable parameters. For example, LoRa. The performance analysis concerned output format, language identification and repetition analysis tasks, knowledge for accuracy benchmarks, and reliability, truthfulness, toxicity, and bias benchmarks. The results showed the repetition problem, the greedy approach of choosing the next token, where the highest probability token is always selected, causes the model to generate a repetitive token sequence, and a decline in reliability. In contrast, the model's knowledge remained unaffected mainly. However, the model was evaluated on only 2 distinct tasks. The existing definition of IL, which we remember was defined earlier, it might even be in this jargon here. Shoot. Well, let's have it build that table for the whole paper. Okay. So we'll have that doing another. So build a jargon table for this entire paper. Include a column with the jargon term and another with a brief explanation of it and anything else necessary and relevant. Okay. There we go. So IL, I forget what that stands for. I think it stands for incremental learning. The existing definition of incremental learning, yeah, that's what it stands for, refers to continual learning techniques based in neural network based models as task incremental, domain incremental, and class incremental learning, depending on whether task identity is specified at test time or is inferred by the model. Task incremental learning learns to solve several distinct tasks. Domain incremental learning learns to solve the same problem in different contexts. Input distribution changes. Thus, the context refers to the underlying distribution from which observations are sampled. Class incremental learning learns to discriminate between incrementally observed classes. The distinction between these scenarios lies in whether context identity must be inferred or whether different contexts contain the same or different classes. The main challenges in domain incremental and class incremental learning are preventing forgetting and correctly identifying tasks, respectively. Incremental learning, assuming that's what it stands for, I'm like 99% sure that is what it stands for, In LLMs,
Comprehensive jargon table extracted from the paper.
and the jargon
Table
table's
includes
ready.
keyterms, acronyms,
Good.
and method mentions along with
So incremental learning should be on the jargon table. Yeah, it's right here. So, yep, incremental learning. So it's the ability of the model to continuously learn and update its knowledge over time as new data or tasks appear without forgetting previously learned tasks, also known as continual or lifelong learning. Okay, cool. All right, so incremental learning in LLMs can also be classified as offline IL and online in-context learning, considering training data sources. Offline IL, while allowing for specific adaptation in new annotated data sets, for example, supervised fine-tuning and RLHF, has its limitations. It requires frequent model updates for evolving tasks and scenarios, and static post updates are inflexible to adapt to real-time changes. Online in-context learning assumes an LLM interacts with an external AI model or agent, or with an offline or online knowledge source. For example, RAG, which stands for Retrieval Augmented Generation. So it's like the ability of an example of like a organic intelligence, like a person, a human using RAG, would be like looking up thesaurus to try to use a wider variety of words. Such methods depend on external knowledge and do not retain persistent learned information, which may lead to loss of used knowledge. So a lot to go in this paper. This is going to take me at least until Friday. I could probably get it all read. Everything I need to read to apply to the job I can probably have done by Friday, but there's going to be... I'm on page 7. Okay, but with that, I've bursted through the hour mark. I can usually I'm only good for an hour on these videos, but if I do Pomodoro and I take a 15-minute break, I'm usually good for about 3 hours. I've found, so I'm gonna do that. I'm gonna take a 15-minute break and come back, and I should be able to make this video about 3 hours. All right, I'm back. I feel shockingly good, so I should be able to do another hour here. So diffusion-based class, incremental learning. Diff class uses diffusion models, DMs, generative models that produce synthetic samples to improve the classifier performance in CIL learning. So continuous incremental learning, is that what that stands for? I don't know. It's probably in the jargon table. Class incremental learning. So it's a scenario of incremental learning where the model progressively learns new classes without forgetting previously learned ones. So this is commonly addressed in computer vision. So it can learn how to identify a dog without forgetting how to identify a cat. And it's called class incremental learning tasks. DMs generate images in a stochastic process by progressively denoising them. They incrementally introduce Gaussian noise into the input data, a forward diffusion step. The procedure is gradually reversed to generate synthetic samples, which are used to update the classifier by removing the noise from noised input, a reverse diffusion step. Synthetic samples are similar to the real ones. The diff class produces artificial examples using multi-distribution matching, MDM, models to balance the quality of the generated samples and their diversity. The models are fine-tuned using LORA. MDM models, multi-distribution matching models, ensure that the classifier is exposed to a diverse range of examples and maintains its performance in previous classes while learning new ones. Before generating samples, selective synthetic image augmentation, SSIA, enlarges the training data distribution and enhances the model's plasticity. So LORA is one that really escapes me, so let's see what that is. Oh, they didn't make it into the... So it's low rank adaptation, but it didn't make it into the jargon table. So briefly explain LOR. Let's have it. Oh, no, it did. It's right here. So it's a PET technique, which should be in the jargon table. So it's a parameter efficient tuning technique. It's an approach to adapt large pre-trained models by updating only a small fraction of parameters or adding lightweight models instead of full fine tuning. So so it's low rank adaptation, PET technique that adds low rank trainable matrices to the model's weight updates, significantly reducing parameter count for fine tuning. It's widely used in large LLMs. Efficiently in tuning large LLMs. It's a common, yeah. All right, so where was I? Let me read this. I think I already read this part, but I'll read it again. MDM models, multi-distribution matching models, ensure that the classifier is exposed to a diverse range of examples and maintains its performance in previous classes while learning new ones. Before generating samples, selective synthetic image augmentation, SSIA, enlarges the training data distribution and enhances the model's plasticity. The method demonstrates state-of-the-art performance in example-free settings in CIFAR 100, 60,000 images with 100 classes, and ImageNet 100, 130,000 images with 100 classes benchmarks. However, increasing the number of new classes to learn prolongs fine-tuning time. Some approaches integrate PET, which we remember from the jargon table, stands for PET stands for well, let's search for it. Parameter efficient tuning. So it's an approach by updating only a small fraction of parameters or adding lightweight models instead of full fine tuning. So it's like yeah, so it's micro tuning of it. So right, so some approaches integrate parameter efficient tuning, yes, with continual learning. For instance, the study in citation 42 continuously introduces and trains soft prompts for each new task to tackle catastrophic forgetting. However, the prolonged accumulation of new prompts raises scalability issues by introducing higher training costs. Excessive LLM modifications can cause forgetting, while insufficient adjustments make inadequate fits for new classes. Expandable subspace ensemble, EASE, is an approach to PTM-based CIL addressing the above issues. So there's a lot of jargon there. Let's take a look at PTM and CIL. The CIL is continuous incremental learning, right? That's where I think that's what CL is. Let's take a look. Oh no, completely wrong. Class incremental learning. So it's a scenario of incremental learning where the model progressively learns new classes without forgetting previous ones. And then so class incremental learning. Yeah, basically like incremental is like another word for continuous, so that would be redundant if that stood for continuous. It stands for class. And then PTM, let's see what that is. Oh, you know what? It's not... yeah, PTM, unfortunately, is one of those terms that is not defined. Huh. I mean, that typically happens when you're in the weeds with jargon. Sometimes some acronyms just get left behind, where like everyone kind of assumes that they know what that acronym is, but worst case scenario, nobody knows. Best case scenario, you're the only one in the room who doesn't know, and you can just look it up. All right, so let's look that up. Add PTM to the jargon table. Okay, so it's going to add it for us. All right, so there we go. So PTM, where did I see that? I saw that here. It's an approach. So it's an approach to PTM-based class incremental learning addressing the above issue. The expanded model initializes and trains an adapter with trainable parameters encoding task-specific information per incoming task. The model extracts embeddings by aggregating historical features to synthesize prototypes of old classes later. In addition, all adapters extract the prototypes of the current dataset for new classes. Accordingly, separate synthesis of prototypes of former and new classes prevents catastrophic forgetting. Verification on 7 benchmark datasets using that, which is a vision transformer encoder model with 86.4 million parameters pre-trained on ImageNet-21K, containing 14 million images with 21,843 classes as a backbone. I think that PTM stands for pre-trained model. Demonstrated 8 state-of-the-art performance. So this particular vision transformer encoder model is named VIT-B/16-IN21K. However, although adapters are small, 0.3% of the base model size increases with additional adapters. The model, datasets, and experiment details are available here. Okay. I'll star that. Why not? All right, so let's see if I got PTM right. Yeah, pre-trained model. I got it right. So it's a model that has been trained on a large corpus of data in a self-supervised manner, capturing general features before being adapted, fine-tuned to downstream tasks. PTMs serve as backbones for specialized tasks, reducing training costs and data requirements. Okay, so prototype and low-rank adaptation, PLORA, starts from a pre-trained backbone and fine-tunes it using LORA, which remember from the jargon table. Low-rank adaptation. With a small number of parameters to learn new classes in federated class incremental learning, FCIL. FCIL is a method to continuously learn new classes while addressing the challenge of forgetting old classes. It is based on a distributed ML paradigm called federated learning, where multiple data owners or local models collaborate to train a shared or server model. Existing methods propose different loss functions on the client and server sides to alleviate local and global CF, but result in significant memory and communication costs. PLORA, prototype and low-rank adaptation, introduces a shared prototype module for the global server, aggregating, reweighting the local prototypes from clients. The local prototype vectors are derived from prototypes of corresponding class features. Then LORA fine-tunes only trainable parameters and sends them to the global server. In particular, each client uses local data to train LORA, which we remember stands for local... No, it doesn't stand for that. It stands for low rank adoption. I don't know what the O stands for. I guess it's the LO in low. Parameters to obtain prototypes of each class. Only the trainable parameters and the average class feature are shared with the server. The classification bias is mitigated by consulting the variations between the class average feature and corresponding prototypes. The server reweights the local prototypes it received to form the global prototype. PLORA utilizes that same thing that we read about earlier. And when I say thing, what I mean is a vision transformer encoder model as the backbone pre-trained model for server and client models. While prototype and low-rank adoption outperforms state-of-the-art approaches, it has high training costs for data, memory, and computational resources for server and client models. Hence, 3 Mile Island being back open. Which is a good thing, because nuclear power is very safe and very efficient. All right, so few-shot incremental learning, FSCIL. Oh, few-shot class incremental learning. That's important to point that out. Trains a base model with sufficient data. Later, it utilizes the knowledge of base classes to learn of new classes with limited data while preserving the understanding of old ones. Few-shot class incremental learning usually fine-tunes the entire model, being susceptible to overfitting and with reduced performance in learning new classes. The attention-aware self-adaptive prompt ASP framework adds specific prompts between attention blocks as attention-aware task invariant prompts, TIP, and self-adaptive task-specific prompts, TSP. So I wonder if that made it onto the jargon table. No, it didn't make it. Okay, well, no, it didn't make it onto the jargon table. That's okay. I can just have it add terms. Okay, so yeah. The TIP, which stands for Task Invariant Prompts, contains task information common for all classes, old and new. The prompts are constructed by encoding input images strongly correlated with semantically relevant information and weakly correlated with irrelevant image information. It aggregates prompt features for the training data to prevent overfitting by averaging them. The TSP is constructed for a particular image input, combining the average and image prompt features. This way, it fine-tunes only the task-specific parameters and needs sufficient data to train new TSPs, which we remember stand for task-specific prompts, for new classes. All right, so ASP, which remember stands for Attention-Aware Self-Adaptive Prompt Framework, uses a different model. The model is VIT-B/16-1K rather than the model we just discussed earlier, which was VIT-B/16-IN21K. So it uses this new model as the base model, pre-trained on the ImageNet1K dataset, which spans 1,000 classes and 1,281,167 training images, 50,000 validation images, and 100,000 test images. Validation shows ASP, which is Attention-Aware Self-Adaptive Prompt, outperforming state-of-the-art FSCIL methods in returning new classes and mitigating forgetting. However, training costs are high, and learning new classes can drop the performance of previous ones. Mini GPT-4 connects a pre-trained visual encoder and a pre-trained LLM. In particular, it combines a vision encoder, a pre-trained VIT, which don't know what that stands for, coupled with Q-Former, Vicuna LLM, and a protection layer connecting the two models. The linear projection layer aligns the visual features with the contextual ones. It does so in a two-step training method. First, it pre-trains the vision encoder on many image-text pairs to learn vision language skills. Then it fine-tunes the model using a small number of high-quality image-text examples and a predefined prompt template to elicit more natural and reliable NL outputs. Mini GPT-4 showcases compositional vision language abilities in a variety of tasks. These include generating detailed image descriptions, extracting facts from movie photos, identifying humorous aspects within memes, providing food recipes from photos, writing poems for images, designing websites from handwritten drafts, and image captioning. However, the model inherits the backbone LLM's limitations and may hallucinate. For example, identifying the presence of non-existent objects in the image, especially with longer captions. The model and data can be found on GitHub as well. Okay, so I can star this. So let me star that. Cool. Okay. All right. So let's try to get to page 10. All right. So the generative multimodal model (GMM) framework for class incremental learning generates detailed image descriptions by incorporating visual and contextual information with a customized generative model. The model contains an encoder producing image and text embeddings, which are further processed by an autoregressive decoder to generate image descriptions. Then it uses a text encoder to produce textual features from the image descriptions and matches features to decide on a label that is highly similar to the prediction. The framework employs bootstrapping language image pre-training with frozen unimodal models, BIP, a vision language model pre-trained from existing pre-trained image encoders and LLMs with significantly fewer trainable parameters than existing methods. The model bridges modalities using a lightweight querying transformer, learning vision language representation with the autoencoder and vision to language generation with the language model. GMM is evaluated on three few-shot class incremental learning benchmark data sets with improved classification accuracy regarding the state of the art while significantly less forgetting. So it has better accuracy with less forgetting. However, the main challenge is transferring the generated textual information into classifying distinct categories. The framework details are available here, so that's probably another good thing to add a star to. All right, so the incremental prompting INC prompt utilizes flexible task-aware prompts to effectively represent task-specific information and mitigate the catastrophic forgetting CF of old tasks. It implements an attention-based transformation of the token sequence, whose results are passed to a group of FF layers, which I forget, escapes me, with a nonlinear activation function named the prompter to generate the prompt as a key and value components. I feel like it's Well, let's add it to the jargon table. Experimental evaluations on these two benchmarks, the first one being Split CIFAR-100, which contains 60,000 images in 100 classes, and Split ImageNet-R, which contains 30,000 images in 200 classes. So experimental evaluations on those continual learning benchmarks showed improved performance over existing methods. However, its scalability concerning task number and data complexity and generalizability to other CL scenarios with different data distributions remain unclear. Okay, so I feel like this could be my second question here. Remain unclear. So why do they remain unclear? I'm just curious about that. Okay. All right, let's get to page 10. So, instruction-based continual learning, INSCL, replays data for each previous task based on their similarity calculated as Wasserstein distance, WD. The instruction embeddings are produced for pairs of tasks. And FF, I think this means feed forward. Let's add this to the jargon table. All right. The instruction embeddings are produced for pairs of tasks, and the proportions of instructions for each task are calculated as probability distributions. In particular, when learning a new task, a replay dataset is formed by sampling examples from previous tasks, where the size of the datasets is estimated as Wasserstein distance between new and previous task training data distributions. The number of previous examples to replay is determined based on their similarity with the task at hand. Moreover, it introduces the instruction information metric, INFO, to measure the instructions quality and diversity and guide the replay process to use high-quality data. Evaluation of 16 distinct tasks, classification, coding, sentiment analysis, QA comprehension, dialogue generation, and summarization, among others, with specific training orders, demonstrates consistent performance improvements. However, INSCL requires high-quality instruction-based data, where fuzzy instructions can affect the task similarity calculation and decrease its performance. All right, I am on page 10. That is good. So let's see here. Let's see if there's like some kind of like, 3 blue, 4 brown sort of video on this. There's a Wikipedia page. So here's one. Yeah, here's one in 4 minutes. Let's do this one. And let's see the new jargon table. Yeah, feed-forward layers, yeah. So neural network layers, typically following attention layers in transformers, performing linear transformations and non-linear activations on token embeddings, often part of transformer blocks in LLMs. Okay, and let's hear about the basics of this.
Now we go to our third measure, which is the Wasserstein distance. And here it only supports the continuous features. When it comes to the intuition or the analogy, it has a few other names such as earth mover distance, and I will describe shortly why it can be called earth mover distance, because it has a very nice physical interpretation. And unfortunately, it's in the range 0 to plus infinity, so you cannot that easily quantify how strong the drift actually is. So now, going to the intuition. It has beautiful physical interpretation, which is the Hollinger distance is just the amount of work needed to transform one distribution into the other. So imagine that the distributions are like piles of dirt. And one pile of dirt is the reference probability density function, and you have the analysis probability density function. And if you were to transform one pile of dirt into the other, and you would calculate the amount of work, which is actual physical equation for the work, and it would give you the Wasserstein distance between two distributions. And the way it's calculated mathematically is the area between the cumulative distribution functions, so CDF that you see here. Quick reminder, PDFs, so probability density function, just give you the density of probability function, so how likely is a given value to fall between any two of the starting point and the end point, and the cumulative distribution function is how likely it is for a value to be at or below a certain point. And here the shaded area is literally just the Wasserstein distance, so it's one of the easiest one to understand. And since I mentioned that it is the amount of work needed to transform one distribution to the other, imagine that you have files that are almost on top of each other, or distributions that are almost on top of each other, except one of the distributions has a small pile of dirt, small outlier, very far away. It would still take a considerable amount of work to transform one into the other, just because there is some outlier really far away. And that means that the distance measure is sensitive to outliers, which might be a good thing if you care about outliers and you want to basically capture all of them. But of course, it can increase the amount of false positives if outliers happen in your data and they're quite normal. So something to bear in mind when you choose which measure to use. And the result here, you see that we don't have outliers in our trip distance feature, and there's only one place when we have an alert, something to look into, and we'll go deeper into the results later on.
All right. Well, that was interesting. All right. That was kind of beyond me. All right. All right. Well, I'm on page 10, so that's a goal. So what am I at now? I'm at the half-hour mark. All right, well, let me take a really quick break here, just like 5 minutes, and I'll be back. All right, that's exactly what I needed. I feel like I can go another half hour really easily. The study in citation 67 presents an interactive continual learning, ICL, a framework inspired by the complementary learning system theory. ICL, interactive continual learning, utilizes interactions among different models. Specifically, it explores the interactions between VIT, simulating System 1, and MLLM, being System 2. And this is based on, so thinking fast and slow. That's what is meant by System 1 and System 2 there. It adapts System 1 parameters while keeping System 2 parameters unchanged. System 2 handles complex examples and interacts with System 1. The class knowledge task, multi-head attention, CKTMHA module enables continuous VIT, so System 1 fine-tuning using category features and from class task collections. This way, System 1 retains old parameters, avoiding ineffective updates. The von Mises Fisher outlier detection and interaction, VMFOID, which is acting as... Okay, well, I don't know what this is. Mechanism estimates sample complexity so that System 1 can select complex enough examples. The examples are used for System 1 inference, whose predictions represent background knowledge for System 2, thereby coordinating the two systems. System 1 uses that model, so -IN21K, as a backbone, whereas System 2 employs Mini GPT as a base model. ICL, which stands for Interactive Continual Learning, was evaluating using CIFAR-10 base classes with 50,000 training and 10,000 class color images per class. CIFAR-100, 100 classes, 500 training, and 100 testing images per class. and ImageNet-R, 200 classes, 30,000 images. The evaluation was conducted in both TIL and CIL settings, and showed CF resistance and superior performance compared to existing methods. However, the limitations of the backbone models restrict the performance enhancement of System 2. The framework is available on GitHub, which is so cool. Everything's just out there. It's like, no wonder this has so much like potential behind it, because people are sharing everything. It's not behind a paywall like everything else. Like, you don't need Sci-Hub to do this. I didn't get this paper from Sci-Hub. I got it from the journal where it was originally posted. All right, so incremental vision language object detection, IVLOD, adapts pre-trained vision language object detection models, VLODMS, to different domains while preserving their general capabilities. The method employs zero inference reparameterizable adoption, ZIRA, with zero inference loss, ZIL, which is kind of a funny acronym for it. The reparameterization techniques for IVLOD without occurring computation and reparameterization techniques for our IVLOD without incurring computation and memory costs. In particular, it retains the original model parameters and adds a parallel branch component, reparameterizable dual branch -RDB, for tuning on downstream tasks without overriding existing knowledge. Based on the RDB's dual branch structure, the ZIL component reduces the inference of new knowledge on learned knowledge by penalizing the RDB's output. The RDB learns new tasks while protecting pre-training and downstream task knowledge. The IVLOD uses a SWIN transformer as a backbone VLM. The evaluation demonstrates that ZIRA preserves VLODM general capabilities while accurately learning new tasks, outperforming state-of-the-art object detection models, including CLDER and IDER. However, the enhanced performance comes from an increased model size. The study on knowledge editing, KE, for LLMs presents practical and efficient methods for modifying and evaluating LLMs post-training to learn new tasks or correct outdated information. These models, such as knowledge insertion, modification, and erasure, are designed to allow on-the-fly model modifications while maintaining overall performance across various inputs. In analogy to the types of human learning, KE knowledge editing methods are categorized as 1. Recognition, exposing the model to new knowledge within a relevant context. 2. Association, forming connections between the model's new knowledge and previous knowledge in the model. 3. Mastery, the model acquires and utilizes the knowledge through its parameters. However, the above methods focus on LLM's components, memory, retriever layers, and parameters, which reflect correlations rather than explicit knowledge. In particular, recognition as resorting to external knowledge is implemented by expanding LLM's layers, for example, feed-forward networks, and parameters, for example, LORA, which I forget. That's a new one to me. I wonder if it's in the jargon table. low rank adaptation. The association is realized via user interactions with the LLM without retraining as additional memory of instruction examples. In other words, various prompting techniques. Mastery manifests through cost-efficient alternatives to fine-tuning. For instance, meta-learning methods edit the model by learning the change in the model instead of updating the weights directly. Model editor networks using gradient decomposition, MEND, uses the rank 1 decomposition to split the model into separate rank 1 matrices to compute the change of the weights, reducing the number of parameters but failing on multiple edits as it ignores the conflicts between them. Some techniques try to locate where the knowledge was stored and edit that part of the model. For example, feed-forward networks area or a set of model weights. However, the side effects are unclear as the underlying LLM mechanisms still need to be clarified. A framework of KE methods, which stands for knowledge editing, and benchmarks with datasets is available here. So might as well star that, why not? All right, now we're gonna talk about the next study in the citation. So we're at the that took 10 minutes. I kind of feel like I'm a little bit running out of steam here. So it looks like there's no chapter. Okay, so the next section is. Oh, and here's where PET gets defined. Yeah, there's a lot of pages to get through before getting to a logical stopping point. So I'm going to have to stop in a place where it's not so obvious to stop. Yeah, so this is where I am now. Okay, well, you know what? I can get to the 2-hour mark. I feel like that's the best I can do for this video. It's going to be a marathon, not a sprint. So, I should take the win and not make sure I can come back to it tomorrow or maybe even later today than just trying to get it all done in one large 10-hour chunk. Like, this is not sustainable. All right. The study in citation 80 examined how pre-trained language models, PLMs, tackle out-of-distribution, OOD data in continual learning scenarios. I do need to sit down. In particular, the model without fine-tuning has poor generalization to out-of-distribution data while performing strongly on in-distribution data, ID data. Thus, it must learn from a data stream containing new unseen examples over time. It fine-tuned 2 transformer-based architectures, GPT-2 decoder with 110 million parameters, and Roberta encoder with 135 million parameters on 2 downstream tasks, predicting API usage and API call. The datasets with API usage sequences were collected from GitHub as Java programs managing one of the associated APIs, 10 million samples as ID to pre-train the models, and 147,000 examples as OOD, which is out of distribution, to fine-tune the models continually. Reply-based and regularization-based CL techniques mitigated CF to some extent while maintaining or slightly improving PLM's performance in downstream tasks. The work builds on a carefully selected ID/OOD scenario and cannot guarantee generalizability on novel unseen examples. Information on the data sets, pre-training, and fine-tuning is available here. All right, so research from the work in the citation numbered 81. Pre-trained and evaluated the T0 model with 3 billion parameters on 50 datasets related to 50 distinct textual QA, classification, and summarization tasks, 100,000 examples for training per task. The model was extended to and verified through CL on 8 new language generation tasks, for example, headline generation, text simplification, and haiku generation. On the one hand, the resulting model demonstrated acceptable performance in learning new tasks, for example, concept drift, while maintaining nearly 100% of the initial performance. On the other hand, the study showed that CL emerges from the intensive pre-training stage. Moreover, in cases where the number of tasks to learn would grow by several orders of magnitude, the users should explore more sophisticated methods for efficiency reasons. The model information and results are available here, so no harm to... well, the harm would be it clutters up all my stars, but I'm going to start anyway. All right, so progressive prompts as cited in the 83rd citation. It's a technique of learning a soft prompt per task, concatenating it with the learned prompts while keeping the base model unchanged. The goals are to keep the knowledge of previous tasks and allow the transfer of existing knowledge for new tasks. The model parameters consist of the fixed PLM, pre-trained language model, parameters, and fine-tuned prompt parameters. The study used an encoder-only BERT model and an encoder-decoder T5 model on text classification tasks. The proposed approach eliminates the need for data replay or storing many task-specific parameters. It shows superior performance on a standard text classification CL benchmark on longer CL sequences spanning 15 tasks. Nevertheless, the model size grows when the number of new tasks increases. I-CL is commonly used to perform diverse language modeling tasks in underrepresented languages, using only short in-context information to narrow the gap between high-resource and low-resource languages. The study from 8.5 investigates the performance of few-shot in-context learning LLMs in low-resource languages. It outlines multilingual LLMs challenges in generalizing to low-resource languages compared to mid- and high-resource languages to emphasize the importance of cross-lingual prompting. Relatedly, it proposes the cross-lingual in-context learning X-ICL method, which combines cross-lingual and in-context alignment, injecting a label aligner, translating the source labels into the target ones to the prompt in between the in-context exemplars and the input query. Alignment, formatting, label configuration, and cross-lingual retrieval methods, retrieving one or more labeled source exemplars semantically relevant to the targets. To propose a query alignment technique enhancing model performance on different language resource levels. X-ICL underwent an evaluation using Bloom-7b and IGLM-7.5b as baseline multilingual LLMs on 25 low resource and 7 relatively higher resource languages across 4 different datasets for topic classification, NL inference, and sentiment analysis tasks. The results show improved performance compared to the baseline models. However, the method does not enhance the inherent capabilities of the deployed LLMs. Moreover, it has limited coverage concerning low resource languages, datasets, tasks, and chosen LLMs. Multimodal LLMs, MLLMs, learn incrementally by using specific techniques such as multimodal instruction tuning, MIT, multimodal in-context learning, MI-CL, and multimodal chain of thought, MCOT. MIT, multimodal instruction tuning, uses instruction formatted data to fine-tune pre-trained LLMs. The model learns new tasks by following novel instructions, wherein instruction formatted sample contains an NL sequence describing the task in an input-output pair. However, instruction tuning from textual LLMs to multimodality adds to the complexity of the learning pipeline in terms of the enlarged datasets or additional models, which further increases the computation burden. For example, aligning embeddings of different modalities directly to the LLMs, or resorting to other models transforming different modalities into NL content that is usable for subsequent LLMs. For example, vision to text for image understanding. In addition, insufficient alignment between visual and textual modalities can increase the risk of hallucinations, providing statistically valid but factually incorrect answers. MI-CL differs from traditional supervised learning, which extracts patterns implicitly from underlying data and learns from analogies. Specifically, it uses a few examples with optional instruction, extrapolating to unseen tasks at the inference stage. Nevertheless, scaling up the context size increases the computation burden on LLMs, whose input length is usually limited. And I'm having the issue I usually have when I read, where even though I'm reading out loud, my brain is, I'm becoming very mechanistic in my reading, where I'm simply formulating the words and my cognition is elsewhere. So that's a sign that I've kind of hit my limit. The idea behind MCOT, which remember stands for multimodal chain of thought, is to prompt the model to generate the reasoning process and the immediate output, resembling human cognitive processing. Although COT can produce results that stimulate human reasoning by crafting a sequence of logically coherent user prompts manually, LLMs do not pose reasoning capabilities by their internal workings. The catalog of MLLMs, multimodal LLMs, can be found here. So that looks like a good one to star. Star that. Cool. That's cool. It's all out there. That's what I like about this so much. Nothing is hidden away. The study from citation 91 introduced evaluating multimodality EMT for measuring CF in MLLMs. The EMT framework. So this is the EMT framework is called Evaluating Multimodality. Employs MLLMs for image classification. it prompts the MLLM to classify the input image based on the text image pair and evaluates its classification accuracy using another LLM. The study also investigated the hallucination effects when fine-tuning LLAVA pre-trained MLLMs. The majority of the open source MLLMs tested, including Lava, Otter, Instruct Blip, and Lens, do not achieve a level of accuracy similar to their base vision encoder performance on standard image classification tasks. Moderate fine-tuning, I do not remember what that means. It's a fine-tuning technique. Improves the Lava's performance on similar non-fine-tuned tasks, aligning visual and text features early. However, progressive fine-tuning can using one dataset decreases Lava's performance by overfitting and hallucinating. For example, producing text related to the data set used for fine-tuning and not to the input question. Okay, so this is a fine-tuning method. So it's low, I think this stands for low something augmentation, low something augmentation. It's a way of fine-tuning the model. Low rank adaptation. So I got the first one right. Okay. All right. So visual instruction tuning uses machine-generated instruction following data to improve LLMs in the language-to-image tasks. It extends instruction tuning to connect vision and language understanding with models like Lava, Large Language, and Vision Assistant. Lava 1.5 architecture contains a pre-trained visual encoder, a pre-trained LLM to interact with users, and a vision language cross-modal connector to align the vision encoder outputs to the language model. So this would be a good one for building like a juggling coach. The model improved baselines on QVA, visual question answering, tasks that answer an NL question about visual images. The results also suggest that visual instruction tuning is more critical in improving the LLM's capabilities than pre-training. Although it requires high-quality targeted visual instruction tuning data, Besides, it could not process multiple images due to insufficient instruction following data. It incurs high computation costs, being trained on 600,000 image text pairs in approximately 1 day on a single A100 machine. Yeah, so that's a good machine. That's a dang good machine. But it's not exactly an H100. All right, so let's star that. But this one is a good one because this one would enable me to write some sort of software for a juggling coach, probably, which I've been wanting to improve upon. And my hometown, Madison, Wisconsin, was involved in this research. Cool. Let me put that under hobbies, juggling. Yeah, let me put that in my juggling folder. Okay. And let's take a look at the, oh yeah, see you can't let's ask the model how much it thinks this costs. It's going to be pretty expensive. I have to wash out a glass. I'll be right back. All right, so a single, yeah, it can cost 10 to 20,000. So that includes a special motherboard and stuff. So all the components together, including all the special components to allow them to integrate, means it's going to be at least $150,000, more like $250,000. So this tiny machine here that fits on your desktop, fits on your desk, that's going to be about $250,000. That's just where we're at nowadays with this. Like, you know, this is cutting edge stuff. It's expensive, and this isn't even cutting edge at all. This is, you know, this is nothing. It's $250,000. Man. Here's a workstation. Okay, here's a deep learning workstation. They got a bunch of different options. Let's go with this one. Yeah, see, if you have to ask, you can't afford it, right? Yeah, you have to request a quote. It's gonna be at least $10,000 for the cheapest machine they have available on their site. All right, well, that places me here, and that places me at the 2-hour mark. So I'm kind of reading pretty mechanistically now. My internal dialogue as I read is becoming less and less sophisticated and more absent. It's more like I'm daydreaming while I read. So I'm becoming a lot less. I think I'm retaining a lot less of what I'm reading now. So I could do a number of things. I could try taking a 15-minute break and coming back after that. I could end the video and come back and work more on it tomorrow. Or I can end the video and come back and try to work more on it later tonight. I think the most logical thing for me to do is to just end the video and take a more comprehensive break and start and do something else. So I'm going to do that. And when I come back, I'll start reading on page 13. So thanks for watching and see you in the next one.